Welcome back. Now, in the previous video, we introduced the Frobenius method. It was a method of doing a series or power series expansion around singular points for an ordinary differential equation. Now, we saw that it came with a few caveats, the biggest of which was that we have to expand around a regular singular point. Remember, there were two different kinds of singular points. There's regular and irregular. Now, unfortunately, irregular points are a whole different beast on their own. So we're only going to focus on regular singular points, and that's what we'll continue to do here. Now, what we also saw with Frobenius's method is that the power series isn't the same kind of thing that you're used to. It's not what you always see of just expanding in polynomial or monomial powers. We saw that there's a little augmented term, r, which we call an exponent at infinity. And in particular, that gave us series that were kind of strange. If you think back to the end of the previous video, we had an exponent of 1/2, which meant that our series was a0 times x to the 1/2 plus a1 times x to the 3/2 plus a2 times x to the 5/2. And so the exponents aren't, your usual 1, 2, 3, 4. Now, other than that, it's pretty okay, right? We can work with this. So what we're going to do is we're going to take a slightly deeper dive into these series solutions near singular points, and we're going to focus on a very famous differential equation. It is called Bessel's equation. We're going to focus on a particular parameter regime of Bessel's equation. We're going to see how we can apply all of the theory that we've developed so far to this extremely important equation. As a side note, Bessel's equation comes up everywhere. Almost any research level mathematician working in partial differential equations has encountered Bessel's equation at some point in their research. I am going to put links in this video description to two of my recent papers where I've actually used Bessel's equation, just so you can see that it is not a totally useless thing. Right? It's an extremely important equation that we are going to actually get to solve using our methods today. Okay, but before we get there, let's remind ourselves what we were doing. We have a second order ordinary differential equation. We are going to assume that the regular singular point is at x naught equal to 0. Okay, that allows me to simplify how I'm writing this. Okay, and then plus x and then x. We're going to call this little p of x. Little p of x is typically your capital Q divided by capital P. And similarly, we have x squared little q of x, which is typically your capital R divided by capital P. Okay, so all I did is I went ahead and divided off the capital P term, and I multiplied through by the x squared. Now, why is this important? Well, we saw previously that this thing is analytic, and so that means that we can write it like this. Xp of x has a power series formulation, and we're going to write it as p sub n x to the power of n. It's an analytic function, so we can always do that. Same thing right here. X squared q of x can similarly be written as a power series. And I'm going to use the coefficients. I'm going to call them q sub n, and I'm going to say x to the power of n. Okay. So then the Frobenius method says the following. So Frobenius says set y is equal to the sum from n equal to 0 to infinity of an x to the n plus r. Right? So this is exactly what we did. And we're going to put this into the ODE. Now, this is going to be very, very ugly, okay? So you can work through the details on your own. I am going to save you a massive headache. I'm going to tell you what this simplifies to, okay? So, from the step that I'm currently on to the next step that I'm going to write, it's all kinds of annoying little details. You can do it. You are a smart individual. I believe that you can work through it. But, for the sake of actually talking about something interesting, I'm going to skip the gory details and I'm going to get us right to a point where we can start having a little bit of fun. Okay, so when you put this into the ordinary differential equation, you get something that looks like this. A naught f of r, I'll explain that in a moment, x to the power of r, plus the sum from n equal to 1 to infinity. And then inside of this sum is a big, ugly thing. So f, same f as right here, of r plus n now, an, plus the summation, and this summation is going to go from k equal to 0 to n minus 1. So it's a double sum. Be very careful. It's a sort of telescoping sum here. A sub k, and then I get, this is going to be r plus k, pk, that's these coefficients from my p term. Sorry, this is pn minus k, pardon me. And then plus qn minus k as well. And then you can close the big square bracket, and this is all x to the r plus n. Okay, so what did I do? All that I did is I put in this series solution. I replaced these by series. I multiplied them all together using the stuff that we reviewed from power series, multiple videos ago. And I cleaned it up so it looks all pretty for you, so that, actually you have a completely general way of viewing this thing. Now, what is f of r? F of r is the indicial equation. This was what we saw in the previous example from the last video. It looks like this. This is the characteristic equation that corresponds to that Euler equation. So I know when we learned Euler equations 2 videos ago, you were thinking, seems a little specific, doesn't really seem that interesting. But they keep rearing their ugly heads. Remember, Frobenius method relies on having this r, and that r is always coming up from the Euler equation. So, in particular, what you get is you get the indicial equation. So the indicial equation, f of r is equal to 0, right? That's what we saw in the previous part of this, or in the previous video. Similarly, this thing right here, all of that. So I don't want to have to rewrite it again because it is just horrible looking. But that is the recurrence relation. Okay, so you can go back and compare with what we did in the previous video for that example that we fleshed out. But in this case, basically, you can get your next coefficient, your nth coefficient, by knowing all of the coefficients up to it. So k equal to 0 all the way up to n minus 1. They're all in here, and they're all sort of put together in a very complex linear combination. But nonetheless, if you know what all of these are, you know what these are from your sums, you can always find the next one. So this recurrence relation is doable. It's just a huge pain, right? It's growing, right? In theory, if these things, are non-zero for every single n. But nonetheless, what happens here? Well, let's remember. So we get solutions. We get solutions that look like this, right? So y1 of x is equal to x to the r1, 1 plus the summation of n equal 1 to infinity. Now I'm going to write this as an of r1, x to the n. Now, why is it that I wrote it as an of r1? Well, this solution to this recurrence relation depends on what the value of r is. So in theory, I could have, I could figure out what the solution of that recurrence relation is for different values of r. It wouldn't be very useful, but I could do it in theory, right? So I don't always have to use r1 here. So that's what I'm trying to indicate, is that This is the solution to the recurrence relation here for that specific value of r. In this case, the root r1 to my indicial equation. Similarly, the other solution, we've already seen this from the example in the previous video. Same thing. It has a solution to the indicial equation, an of r2. But here is something that I bet you I can read your mind about. What happens if r1 is equal to r2? Right? Because if r1 and r2 are equal, this is the same. So we have the same exponent at the singularity. And the solution to the recurrence relation is the same. So I didn't get two solutions. I only got one. But we have spent a lot of time through this lecture series learning the theory of second order equations. And we know that there's always two solutions. So the question is, what is the other one? Well, if you remember how to do this for repeated roots of, say, the Euler equation, you know that you have to use reduction of order. So we use reduction of order. Now, this is punishing to get this solution. So I'm not going to go through the derivation of this. It is very complex. But nonetheless, you could do it if you really wanted to. Remember, if you want to use reduction of order, you set y is equal to a function of x times your known function, your known solution, y1. It's going to be a huge pain, especially if you're going through these massive series. But luckily, I've got a solution for you. y2 of x is equal to y1 of x times the natural logarithm of x, coming up just like we saw for the Euler equations, right? Remember when we had repeated roots of the Euler equations, we saw this ln, or this natural logarithm, pop up. But unfortunately, there's much more. You get something that looks like this. So you still get the singularity that pops out. You go up to infinity. an prime of r1 x to the power of n. Now the question is, what is an prime? Well, I wrote this solution to this recurrence relation as a function of r. We love functions, right? This class is a lot of calculus, and that means that we could actually take derivatives here. So in fact, an prime of r1 is equal to ddr of an of r evaluated at r1, right? So it's a derivative of the solution of the sequence. So this is crazy, right? It is so complicated. It is so ugly. I highly recommend, unless you really are a glutton for punishment, not going through the reduction of order to do that. It is a very complex thing to do. And fortunately, now we've got a formula. Let's actually put it into practice. So what I would like to do for the remainder of this video is I would like to consider Bessel's equation. And this is a particular parameter regime of Bessel's equation. So we typically refer to this as Bessel's equation of the 0th order. This is an equation that looks like this. Plus xy prime x squared y is equal to 0. Okay, so it looks innocent enough, but it turns out to be very complex. Quite ugly, in fact. So let's note something right off the bat, because what I would like to do, instead of doing the whole Frobenius method, I would like to take my general theory from right here and just say, boom, there's all of the things that you were looking for. So first of all, xp of x is equal to 1, right? So if I put everything in terms of what I'm seeing over here, I've got an x, I've got my x squared, I've got my x squared q, And so therefore my xp of x is just a 1 term, and my q squared. So and x squared q of x is just equal to x squared. So that tells me q is just equal to 1. So, how bad could this be? Well, the first thing that we know here is if I take the limit as this goes to 0, as x goes to 0 here, well, then I get p0 is equal to 1 and q0 is equal to 0. Okay? Now, this is, again, very nice, right? So all that I'm doing is taking the limit as x goes to 1, or I could just find the series expansion. These things are polynomials. It's very, very easy. They are analytic functions. I'm just looking for the first term of the series. Now, why is this important? Well, it gives me my indicial equation. Because here now I get r times r minus 1. So where were we? We were right here. R times r minus 1 plus p0r plus q0. So basically just plus r. Clean it up. R squared. And so this tells me that I get a double root here. So I get r is equal to 0. That is a double root, which, of course, I chose this example because it's interesting and it applies exactly what we have right here. So clearly, half of the work is going to be finding y1, and then the other half of the work is going to be finding y2. Well, what I'm going to do is I'm going to allow you to check or to figure out what y1 is. So this is just your standard Frobenius method. So all you're going to do is set y is equal to an x to the n plus r, put it into the differential equation, and solve it. Okay, so I want to leave that for you to have the fun. That is the standard Frobenius method. This is good practice for you. So we find y1 of x. Well, what does y1 of x equal? So after I factor out the a0, I get 1 plus sum from n equal 1 to infinity. And in this case, we find that it only counts up the even terms. So I get minus 1 to the m x, or sorry, to the n, pardon me, n to the 2n, so all of the even terms divided by 2 to the 2n, and then times n factorial squared. So it is something else. It is a pretty wild looking equation here. And just for your own records, the recurrence relation, so if you want to double check while you're going through this, trying to find it, my recurrence relation is given in this way. an of r is equal to minus a n minus 2 of r. That's where I get every second term in this thing. That's why I'm counting up just the even powers, because it is a second order equation. This thing divided by r plus n squared. And in this case, this is for all n greater than or equal to 2. So I highly recommend working through, seeing if you can get to that recurrence relation and use that recurrence relation to find these coefficients, to find that solution. Okay, but what is it that I really want to focus on? I really want to focus on finding y2, because we can see that things are going to be a little bit ugly. Okay, the first piece of this is going to be finding what all of these derivatives are. So first of all, we can find that, so if we want to find y2, the first thing we note, so maybe we can put a note here, finding y2 now. All right, I'm getting a bit of a scatterbrain here because I'm so excited that we're going to go through this. But First thing we note is that A1 of R, A3 of R, all of the odds, these are equal to 0 for all R near R1 equal to 0. Okay, so basically, again, this is telling me that I'm only looking at derivatives of the even terms. Now, this is something that a lot of you might overlook, right? Because just because these things were equal to 0 at a single point, at R1 equal to 0, it doesn't mean their derivatives are. But you can easily check that the same condition that gave you that A1 is equal to 0 gives you that A1 is equal to 0 everywhere for R close to 0. So this tells me that A1 prime of R1 is equal to A3 prime of R1, which is equal to A2n plus 1 prime of R1 is equal to 0, right? These are all constant functions. They have no variation. There is no derivatives that come through here. Okay, that's all right. Now let's keep going. So in this case, we are going to need to have a completely general result here. So if we would like to find what the solution to this difference equation is, we can actually just find a pattern for any value of R. So in this case, we get A2m, so all of the even ones, right? That's what's popping out up here. This is equal to minus 1 to the m, A0, divided by R plus 2 squared times R plus 4 squared, all the way up to R plus 2m squared. Okay, now we have a general solution for any value of R, right? So we have a function of R. You give me R. You give me R equal to pi. You give me R equal to 0. R equal to minus square root of 2. I can put it in there. I can tell you what the solution to my recurrence relation is. Unless R is equal to 0, it has nothing to do with the original differential equation. But that's okay. I can still do it. Now I can take some derivatives. In particular, what I can find here is that, so I'm going to do a little bit of magic, but I can actually find that when I take the derivative of this thing and I divide it by itself, this is equal to minus 2 over R plus 2 minus 2 over R plus 4 minus ... minus 2 over R plus 2m. Okay, so try and see if you can get that yourself. It's just going to be taking all of these derivatives. Every single time you're just doing this sort of quotient rule here, and you're getting out a factor of R plus 1, right? Because you are, or sorry, R plus 2 or R plus 4 or R plus 2m. That's just because you're going to increase the exponent here. That's why I took this a to the 2m, because this term is still going to be here. It would be multiplied into everything here. I just divided it off. So again, pause the video, see if you can get that. This is a very, very fun exercise. But what do I get now? This essentially gives me that when I take a derivative and evaluate it at 0, well, what did I get? I got minus 2 and then times 1/2 plus 1/4. Remember, I factored out the 2's on the top and all the minuses, all the way up to 1 over 2m. And if I multiply this thing back up, I'm going to get, I'll write it on the next line because I don't want you to lose any of this, A2m of 0. So it's getting very, very ugly here. But this minus 2, it's going to knock off all of these even powers. And so this tells me that I get A2m prime of 0 this is equal to minus 1 plus a half plus a third all the way up to 1 over m, and then times a times 2m of 0. Now, this is the first m terms of the harmonic series. So I'm going to use a little shorthand for this. I'm going to call it h sub m. H stands for the harmonic series, right? The sum of 1 over n. This just means truncated at the mth term. But now I've got everything I need to put this into the equation. And therefore, y2 of x is equal to y1 of x. I don't want to have to write it again. It's written right here for you. And then plus, now we get a big ugly sum. So n equal to 0 to infinity. 1 to infinity, pardon me. N equal 1 to infinity. Now I still have the a2m's in here. That means I have these minus 1's floating through. So minus 1 to the n. And then I get my hn term. I just switched my indices from n to m. There's no issue with that. X to the 2n, because I'm only keeping every even term. All the odd ones are falling off. And then divided by 2 to the 2n, and then times n factorial squared. And in this case, this is going to hold for all x greater than 0. If you want this to hold for x less than 0, slap some absolute values around this, in particular in the logarithm. That'll make it work. But look what we've done. We solved Bessel's equation. Now, I left some steps out on purpose. I want you to try and fill in the gaps. In particular, use the Frobenius method to solve for y1. Then see if you can get this derivative relationship here, right? So it might take you a little bit of mathematical induction to work your way up through that thing. That's okay. That's part of the learning process. That's what I want, right? It's one thing for me to stand here and do all the work. It's another thing for you to work through it with me. And it's much more rewarding if we do things like that. The last piece here, this should be a plus 1. And that comes from this minus right here, right? So we get another minus 1 factor in front of the h terms, just multiplied into this piece. And now you've seen it in action. Now you see that it's very, very complicated. And in particular, the hardest part of all of this is finding a general solution to my recurrence relation. Not something we can always do. And because it's not something we can always do, it's not very easy to find what the second series solution is. So, takeaways. Very complicated. Very, very complicated. Of course, we want to stay in the realm where we have distinct roots. Because if we have distinct roots, life is pretty good. Repeated roots, like we see with the Bessel equation, get very, very complicated very quickly. But, if we just put our nose to the grindstone, we can work through it, we can get to that answer, as we did right here.